use the fact that every permutation sigma is a product of transpositions. To prove the following theorem. So, let us write it as a theorem. So, theorem, let f from v power I to w be I multilinear map okay. One, if f is alternating, then f is skew symmetric. Converse is not true, as you can see after this in a small example, but the converse is true when you assume, suppose characteristic of the field K is not 2. So, this means 1K plus 1K, which is 2, is not 0 in the field. Typically this happens for a finite field which is a field extension of the field Z mod 2, which is used in communication engineering and so on. If f is skew symmetric, then f is alternating. Proof. We want to show that f is skew symmetric. So, let us take two coordinates, two elements I and j in the set I, such that I not equal to j. And let us compute. So, recall the definition that it is if alternating means if two coordinates are equal, then the values are 0. So, if I take, if the f is given to be alternating, so if you look at f of, keep the coordinate same other than ith and jth coordinate. Ith coordinate you put x plus y, and jth coordinate you put x plus y again, and whenever I do not write anything, those coordinates are fixed. X and y are arbitrary elements in the vector space V. This is 0 because this is ith coordinate, this is jth coordinate, and they have the same component. Therefore, this is 0 because f is alternating. On the other hand, it is multilinear, so I will expand it. The remaining dot dot coordinates are same. So, f of dot 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 x dot 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 x dot dot dot. So, I have taken this and this plus f y x. So, I have taken y and this x. Now, I have two more things plus f dot dot dot, now y dot 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 x dot 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 plus f y dot 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 y dot dot dot. This is simply because of I use a multilinearity here and multilinearity here. This will give 2 terms, this will give 2 terms, altogether 4 terms. And now f is alternating. So, therefore, this has 2 equal coordinates because x and x both remains at I and jth position. So this is 0. Similarly, y remains ith and jth coordinate, so this is also 0. So the result is together what you get is f of, so 0 equal to f of dot 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 x dot 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 y dot 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 plus f of dot 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 y dot 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 x dot this. So here note the coordinates are interchange. Ith position, this was ith, this was jth, and this they are switched. So that means f of this equal to minus f of, that means we have proved that if I take any tuple and apply the transposition tau equal to ij, then you get the formula f of any tuple x tau I in I, this is same as minus f of xi. So we have proved that for any transposition f of the permuted tuple is minus of the original tuple. So therefore it will follow, because every permutation is a product of transpositions, we follow that f of x sigma I in I, this is same as sine of sigma f of original tuple xi. That means f is skew symmetric. This is true for every sigma. Here that is where we use every permutation is a product of transpositions, as many transpositions as either even or odd, depending on the sign is 1 or minus 1. Now proof of 2, suppose I is not equal to j and x is any vector, and we want to prove that we have given f is skew symmetric, and remember we want to prove that f is alternating. And remember we will have to use the condition characteristic of k is not equal to 2. So that means I want to show that f on any tuple which has at least two different components equal, then f has to be 0 on such tuples. That is the meaning of alternating. So that means I need to prove that if I put x at the ith position and also x at the jth position, then such values are 0. But I definitely know if I switch, that means if I apply a transposition ij, then this changes the sign. This is f of dot dot dot, and these are changed that you can't see it. We have changed the coordinates, but they are equal coordinates, so you cannot see it. So this is minus of that. So that means 2 times, bring this to this side, 2 times f of x dot 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 x, this is 0, but this is an element in the vector space W. This is 2 is not 0 in the field in K. So I can multiply by 2 inverse, because 2 is invertible in the field, so that you can conclude f of this is 0. So that is f is alternating. So, just wanted to remark what happens in the characteristic 2. If characteristic k is 2, that means 1 plus 1 is 0 in k, or equivalently 1 equal to minus 1 in k. Then symmetric is and alternating and skew symmetric. These two concepts are same, and there is no reason for symmetric to be alternating. So, for example, you could take this bilinear form xy equal to x times y. So, this is not alternating. Okay. So, all right. So, now I want to construct first very important remark I want to make. Very important observation. The following theorem. So, theorem let f from v power I to w be alternating I multilinear map then f of a tuple xi, this is 0 for every k linearly independent tuple. Not independent, dependent. K linearly dependent I tuple xi. Note that before I prove this, note that if cardinality of this finite set is strictly bigger than the dimension, then every I tuple is linearly dependent. Every I tuple xi, I in I, is k linearly independent. K linearly dependent. That is because we have proved that every linearly independent subset we can extend it to a basis, and every two bases have the same cardinality as the dimension. So, definitely every tuple which has more elements, more components than the dimension has to be linearly dependent. So, this will mean immediate corollary to this theorem will be there is no alternating multilinear map if this I is more than the dimension, cardinality I is more than the dimension. That means I did not introduce a notation, but I will do it now. If I write alt k I v w, this means all alternating I multilinear maps from v power I to w, then this set will actually be the 0 if cardinality I is more than the dimension, because any tuple the value will be 0. That means F has to be 0 map. 0 map is the only alternating multilinear map when I has more elements. And the next case we will study is when cardinality I is exactly equal to the dimension and W equal to K, and those will be called determinant functions. Before that, let us prove this. So, we have to prove that on a linearly independent tuple. So, proof. So, suppose xi I in I is linearly dependent over K. That means there is a linear dependence relation. So, that means there exists definitely one index I naught in I such that xi naught is a combination of the remaining one, a I xi, I runs in I and I is not I naught. You can always arrive at this equation because dependence relation will have at least one non-zero coefficient, and we are over a field. So, I will make that coefficient to be 1 and then shift to the other side. So, definitely such a dependence relation we have, and now we want to compute what is f of xi. Well, in this I am substituting I naught coordinate. So, it is I naught coordinate is summation ai xi, I in I and I is not I naught. This is the I naught coordinate, remaining coordinates are same as xi. When I use a multilinearity at this I naught coordinate, this will come out. So, this is same as summation. This summation is running over this I in I naught equal to I naught, and these ai's will come out, and remaining will be f of and I naught position xi. This is I naught position. But remember, this is I naught position, and the remaining positions also this is same. There is somewhere else in this ith position is somewhere else that different from I naught position. So, this has to be 0 because f is alternating. For each I different from I naught, this xi is sitting at ith position as well as I naught position, and f is alternating. So, this sum is 0, therefore, everything is 0. So, that is what we proved it. F vanishes on a linearly dependent tuples. Alternating map vanishes on the linearly dependent tuples. Okay, now I want to give a canonical process so that given an alternating map, given a multilinear map f is from v power I to w, arbitrary I multilinear map. I want to give a standard recipe to make this map f to be alternating, not the map f. I will alter a map f and arrive at a alternating map. So, what am I saying? Then if I define AF by definition, this is summation, sigma summation is running over all permutations, sine of sigma times sigma f. So, I have summed it up over all permutations, so that sine multiply sigma f by the sine sigma. Now, I want to check that this AF, clearly this AF is a map from V power I to W. Clearly it is I multilinear because we have checked that I multilinear maps form a subspace. That means if I take different multilinear maps and add them with some scalars, then also I get multilinear maps. So, this is a sum, finite sum, these are multilinear, these are some scalars, 1 or minus 1, and therefore this sum is definitely I multilinear. I want to check that this is alternating. AF is alternating. I multilinear. So I should check that if I take a tuple whose two coordinates at different positions are equal, then the value on those tuples of AF is 0. So I have to check that if I take any tuple xi in V power I with rth coordinate of this tuple is xr and sth coordinate is xs, they are equal for r s in I not equal. Then I want to check that, then to prove or to check that AF on this tuple XR XS, this is 0. I want to check that these are equal, that is given to us. For this I will use the fact that the symmetric group, and remember this is the alternating group AI, these are permutations whose sign is 1, and if I multiply the permutations whose sign is 1 by a transposition RS, then these are all odd permutation, these are all even permutation, these are all sign is, because sign changes, sign is product preserving, this is minus 1, this is all signs here are 1. So, the signs, all signs are minus 1s here. So, they do not intersect, and if you count them, this is n factorial by 2, this is also n factorial by 2. So, they will cover all the permutations. So, this means this permutation group is decomposed as a partition of even permutation and odd permutations which are multiplied by this particular transposition to all even permutation. So, I will use this fact. So, now let us use the definition of AF and compute this left hand side. Remember, definition of AF is summation running over the permutation, all permutation. This summation I will split into two parts, one is here and the other is here. So, therefore, AF at this tuple XR XS, this tuple is by definition summation now running in sigma in AI alternating, and in this case I do not need a sign because sign is 1 in this case. So, that is just sigma f evaluated on this tuple. Then the other sum that will come with minus sign summation sigma running in AI again, and I would have to apply permutation the transposition which changes R to S sigma, and this F applied to this tuple. And of course, the sign which I have taken minus out, this is because of the sign of this permutation is minus 1. But now when you do this, remember these coordinates are same, these two coordinates are same, that is our assumption. So, when I apply sigma f, then still those two coordinates will be equal, and when I now interchange R and S, the difference will not be seen. So, let us apply this. This is the first sum is summation sigma f applied to this. Let me write both are x. Let me write xr equal to xs equal to x. Then this will be x. this is also x, this with the minus sign sigma in ai, this sum is also sigma in ai, and then this will be same as sigma f evaluated on x and x, because when you interchange rth and xth coordinate it doesn't change. This will be f of x, this will be f of x2, so it doesn't change. And I could now club the two sums together, summation running sigma in ai, sigma f x this minus sigma f x this, and this is equal to this, so it gets cancelled, so altogether it is 0. This will get cancelled with this, all the sum gets cancelled, so it is 0. So that proves that f is alternating. Similar construction you can also do it to construct a symmetric operator. See, remember, from multilinear operator we have constructed alternating operator. Similarly, from a multilinear operator v power I to w, I multilinear, if I want to construct a symmetric operator, multilinear symmetric, then simply I could define SF equal to summation sigma in SI, and don't take sign, sigma f. This is again an operator, this is again a multilinear map from Vi to W. I multilinear is obvious because sum of multilinear maps is multilinear. And the same proof what we have checked, this will make f SF is symmetric I multilinear. Okay, with this now we are ready to study what is called determinant functions. So the next topic I will start is determinant functions. So in this section I will prove the existence of determinant functions, and actually what I want to do is the following. Suppose we have a V is a k vector space, and now I want to study, when I say functions, there means they are forms. I want to study alternating forms on V. That means I want to study this object alt I V k. We have seen it is a vector space. This is a k vector space. And now we are a special case, what we are doing is we want to study it when cardinality of I is exactly equal to the dimension of V. Because we have seen when cardinality is more, then this vector space is actually 0 vector space. When it is less, it is little bit more complicated to study, especially I want to compute what is the dimension of this vector space. So this also I will, if you put this as n, this also I will just simply abbreviate by saying ALT NV, alternating n linear forms on V where n is the dimension. And what I want to prove is dimension of this vector space is 1. It is one dimensional vector space. This is what we will prove. In fact, more generally we can prove this. I will not prove in this course, but maybe the next course I will prove that dimension of alt RV, where R is smaller equal to dimension, When R is more than dimension, then we know it is 0 vector space. In this case, it is nothing but n choose R, where R equal to n case is what we are going to do, that is n choose n is 1. This is what we want to prove, and actually we want to construct a canonical basis for this vector space. Given a basis of V, we want to construct a canonical alternating form which will be a basis of this actually. Okay, so this is what the content of this next lecture is. I will, so elements of alt NV are called determinant functions on V. Okay. So, let us recall what I stated some minutes back, the distributive law, and I will use that distributive law to expand this, but that I will do it next time, and I will prove next time the dimension of this vector space is 1, and we will construct canonical alternating maps on V by using the basis tuples of V.